rocket ship on my way to Mars on a collision course. I am a satellite. I'm out of control. All alone in the family of the sun. Curiosity tasting everyone on a home. Learn some from the sun. Out of the silent planet come the demons of creation. The ocean flourishes from birth.
So I'm mostly in everything. How's space?
Hey everyone, this is what the video lectures are going to look like. So as you can see, I'm using software called VoiceThread, and most of the time what's going to be there with the slides is going to be my voice. I won't always do a video, just doing this to show you how it works. So this week the virtual lecture is on the formation of the solar system, and a little bit on the physics of the solar system, although some of that we'll also cover next week. So yeah, we'll go through the slides. I'll add comments as if I were teaching it in a course. And most of these, I imagine, will take somewhere between an hour or at the most an hour and a half, but even shorter than an hour, some of them I'm sure. So that's what the virtual lectures are going to be. I'm sure a lot of your other instructors are using this. So yeah, before we actually talk about the formation of the solar system, I guess it's fair game to ask, why study the formation of the solar system? And a recurrent theme throughout my teaching of this course is that one of the big things that exploring planets and moons has provided us is the ability to understand better, certainly better than we did before the space age, how the solar system came together. And that's a pretty big question. It's a much smaller version of things like the Big Bang and the origins of life and all that, although the origins of life are tied into more certainly the formation of the solar system and the formation of Earth. But this is obviously a pretty big deal for us as a civilization and a species to understand where we come from. And the solar system is certainly a big part of that. So one thing you'll also see is how I wrap up this lecture is that we understand part of the story, at least we think we do, about how the solar system formed, but there's still a ton of mysteries that we don't understand. There's portions of the story that perhaps contradict itself. There's portions of the story in which you may hear different versions. Even some of my timelines that I provide and the timelines provided by Rothery in the reading for this week are a little different, and I'll talk about that. There's still a lot to learn about the solar system. As you can imagine, it's a massive, complex physical system of which we exist inside of. So we have good reason to want to understand it, but it's, again, we're sitting on this one tiny rock inside of it, and we only have so many ways of looking at things to try to figure out how they came to be. So with the Earth, it's not too hard because at least we're on the Earth, but figuring out more than how the Earth formed and where the Earth's materials came from and how the other planets and moons formed and what makes Earth unique and what doesn't make Earth unique is all part of this story. So really, this is all about, for me, the big reason we undertake planetary science or space exploration is to understand this story and fill in the puzzle pieces that we still don't have for this picture. Where this picture starts is with this picture that we're looking at. This is the Orion Nebula, and this is an example of all forms of nebula in our galaxy and in our universe. And what we suspect took place about 4.5 billion years ago, actually even longer than that, 4.6 to 4.7 billion years ago, is that some pocket of gas and dust in this cloud, or a cloud like this, would have segregated itself and separated, as is often the case, to start forming a cluster of what would eventually become a bunch of solar systems. So if you see here the bright dots in between, I think I can circle them. But if you see these things forming, these are star clusters. And essentially, this is where you're getting little balls of gas and dust forming and kind of concentrating, almost like a snowball. And we'll talk about a snowballing process called accretion quite a bit throughout this lecture. So that's where it all kind of starts. The universe is filled with gas and dust, much of it very far from one another. But if you zoom out far enough, as this kind of large astronomical picture does from the space Hubble Space Telescope, you can see that if you zoom out far enough, some of the gas is at least relatively close together and starts to get even closer together. And that's when we start getting things like stars, where there's matter very close together. So this is the beginning of it all. And like I said in the intro, we don't talk about astronomy a lot. This lecture is pretty much all of the astronomy we talk about in this course. That is to say, things about stars and giant nebula, which is just clouds of gas and dust. But when we talk about the formation of the solar system, we kind of have to, because that's where it all begins. So here I'm definitely explaining it a lot, perhaps better than I just did, give you some text to digest. So first of all, when we talk about dust in the context of astronomy, it's really tiny particles down to the atomic level in some cases. And in the Orion Nebula, we get this kind of dust cloud building up, and it's hundreds of light years across, and part of it begins to collapse, and clusters of future stars separate. And this is really where our timeline starts. So everything from here is after collapse. And this collapse is really meant to say, okay, there's this giant dust cloud that kind of pulls away from an even bigger dust cloud. And this little dust cloud that pulled away starts to collapse. That's time zero for us in this lecture. You'll see in the Rothery chapter that his time zero is actually the formation of the sun, which is a little bit of different time zero. But because these times are not that far apart from one another on an astronomical scale, we'll say, at the end of the day, we all get to kind of the same 4.5, 4.6 billion years ago in which the solar system started. So we have this collapse of dust starting to fall upon itself through mechanisms, well, through mainly the mechanism of gravity and other fundamental forces of our universe. And 50,000 years later, we get a circular motion, and this little breakaway clouds kind of flattens out, and we get a disk. Well, 90,000 years after its collapse, we get a disk, and this is really the beginnings of our solar system. This is what that disk starts to look like, and this should look kind of familiar. This is a lot like this is our baby solar system, an artist's rendition of it, of course. And this is the sun in the middle, although where we are in my story right now, that sun should be kind of a glowing red, not a yellow yet. And we have kind of waves of dust and gas surrounding it, which have been flattened out through a form of centrifugal force. So we have this swirling in a counterclockwise direction. We have everything moving around the center, which is where the sun is. And this sun has formed because the center of gravity of this cloud is where stuff starts to stick together the fastest. And that's where the sun forms. It's the first thing to form in this emerging system. So we get now what we call a proto-star. This is the beginning of a star. I like to reiterate kind of the process or the story as it unfolds. You get this little ball of dust that breaks away from a giant nebula. Because of the centrifugal force of the universe, it starts to kind of rotate and flatten out. As it does that, the material in it, a lot of it goes to the center. It moves inwards, as with anything else in our universe, where there's centrifugal rotational force. And our entire universe appears to be spinning, so everything in it also spins. And all that material in the middle forms a little baby sun, the proto-star. And this is red. This is a red dwarf at the time. It's the name for the stage of a star at this age. If you're more interested in that, how stars form, certainly take an astronomy course as well as this course. And we now have this flattened out disk at the middle, there being a little baby star. And eventually, through a result of through a result of nuclear friction, we get heat generated by this star. And because this star is now giving off of heat, we get things that are close to it being evaporated. We get a little bit of proto-solar wind, and we get a very important delineation in this early system, this disk. We get, obviously, the middle is the protostar, and about 80 million kilometers away from that, or about half the distance from the Earth, so 0.5 AU. Remember that AU is an astronomical unit, the distance between the Earth and the Sun. So about half that, there's a little kind of imaginary border, and on the inside of that, you get kind of metals and minerals forming. On the outside of that, you get kind of metals and minerals forming. Everything on the inside of that is kind of evaporated or vaporized because of the heat of this little baby sun. And then further out, you keep traveling away from the sun, about 400 million kilometers away, or about 2.5 AUs away. And I apologize, the text there is cut off. I should have buried the picture beneath the text. My apologies. You get this ice line. And this is, again, about 400 million kilometers away from the protostar, 2.5 AU. And this is the point in which everything on the inside of it can't really form what we call ice. And ice in the solar system context is any kind of frozen, well, certainly liquids and frozen gases. So not just water ice, but carbon dioxide ice, and nitrogen ice and methane ice and things like that. So none of that can form, but on the outside of this line, on the other side of it, away from the sun, you do get the formation of ice. So you get hydrogen particles bonding with other things and freezing. Of course, if they bond with oxygen, they form water ice. You'll see in Rothery, the reading for this week, you'll see a distinction. You'll see he mentions 5 AU as the point where the ice line is, the point in our solar system where on the inside of it, ice melts. On the outside of it, ice freezes. And of course, this is assuming it's exposed to the sun and not protected by an atmosphere like on Earth. But of course, 4.5 billion years ago, there's no atmospheres around to talk about. And the sun is a lot weaker. So at formation, the ice line was 2.5 AU from the proto-sun. Now, with the sun in its full phase, or certainly much more powerful than it was early in its life, the ice line has actually moved out. So within 5 AU, ice unprotected by, say, a magnetic field or certainly an atmosphere, vaporizes away. This is what we see on asteroids, even comets that pass into the inner solar system, and planetary bodies as well. So that the ice line has shifted over time, but at the formation of our solar system, it was just about 2.5 AU away, which is roughly where the asteroid belt is. So here we have a visual representation of the ice line, or here as it's called, the frost line. And I recognize that, for the students taking astronomy as a major, this is probably painfully boring and obvious, as you've probably studied the formation of not just our solar system, but solar systems in general. And then for students certainly not in astronomy and not even studying things like physics and whatnot, this can be perhaps a bit confusing, or using a lot of terms that, well, we're not going to use for much of this course. And, the key for this lecture is to really understand the the formation of our solar system, the general storyline of how it came to be. There's a lot of details I'll provide along each slide, such as the distance of the ice line and why it has shifted over time and why different sources will have it listed differently. And even which elements are freezing on which side of it and all that. And you'll also see that in Rothery this week and in the reading next week as well. And, you know, those details are good, and they can certainly, if you latch onto them and apply them in the right places, will definitely help make your final project and all the assignments along the way much better. But the one thing you definitely want to come out of this lecture with an understanding of is the basic storyline. So again, the details, you may go back and grab them as you need them for your assignments, but the general storyline you really need to grasp in order for the rest of the course to also make sense. And then therefore for you to be able to do better on the assignments throughout. So again, details and stuff flowing your way. I understand it can be hard to pick up the first time, but really this first run through the origin of the solar system, just focus on the general storyline. So we have, again, gas cloud breaks away, starts spinning, flattens out. In the middle, you get a star, which is our sun. It starts to kind of clear away the material closest to it by evaporating it or vaporizing it. A little further out, you can get things like ice forming. A little closer, you can get things like little baby rocks forming, and Rothery talks about that and why oxygen can bond with silicate, which is really what most rocks are made out of. So you just get different things happening at different distances from the sun, which all makes sense, I hope, to your basic understanding of physics as well, right? Obviously, things like ice aren't going to form close to the sun. And a lot of the heavier materials are going to be pulled towards the sun, which means that a lot of the materials that would be involved with rocks might be on the inside. But we'll see that there's some challenges. That's one of the difficulties or I'd say mysteries to an extent of the solar system. So all that to say, this is a visual representation of the ice line. And again, you can see here the hydrogen helium gas nebula. We'll talk about hydrogen helium in a second. Both abundant gases in our, well, we assume universe, certainly galaxy and certainly solar system. We'll see the role of helium in a second once the sun goes yellow. But right now, most of what's happening in the sun is a bunch of hydrogen being pulled towards the center. And as it does so, you get this kind of nuclear friction, which gives off heat. Now I say we go into the very kind of intuitive part of the solar system forming. And again, it looks like the image got, I think when I upload the images to VoiceThread, they kind of get distorted because I don't remember covering up the text with the image here, but that's no problem. You can see what it says, planet to begin. And so, yes, throughout this process, we've had particles hitting other particles and starting to make bigger particles. And eventually we get things that if we were around at the time, we could see with our naked eyes. They grow larger than the microscopic scale, and we get things like little rocks and whatnot. And well, that actually takes a little while, I should say. So these particles begin to collide. They stick together through a process not that much unlike static electricity. So they're pulled together by the fundamental concept of gravity, but they stick together not necessarily through collision and kind of combination, but more because of static forces, which kind of hold them together electronically. So in the outer solar system, this occurs much more because there's more stuff. I'm hesitant to say stuff that's necessarily solid. There's a lot of gas out there. That gas can add to this. Certainly if you had oxygen and silicates, you can get the ices on top of the rocks. So then you do have more stuff in the outer solar system, whereas the inner solar system, it's really just the stronger elements that have not formed ice, obviously because they can, it's too hot. So you get things like silicates and rocks. So this is all taking place by about 2 million years later. So 2 million years after collapse, the initial collapse, which started this all, we get the earliest planetary formations. And a million years later, we get the earliest things that we could even call planets, or in this case, planetesimals, which just means very small planets. And they're kilometers across, so what today we would call asteroids. Quite large asteroids in some cases. Even Rothery references the potential for planetesimals to have been 10 to 100 to thousands of kilometers in size. But at that point, we would probably call them protoplanets. Not that these terms, well, I suppose you could find a planetary scientist who's very strict about them, but in most cases, you'll see these terms used varyingly. So this sticking around, or the sticking to each other, and these little planetesimals forming and colliding into each other, and sometimes making bigger ones, and this all carries on for a few million years, which now seems like a long time, but back then is nothing, because we're still talking about 4 billion years ago at this point. Well, 4.5 billion years ago at this point. So we're talking about a long time ago, but in a comparatively short period of time, 6 million years after the collapse, we do get 2 of these very large protoplanets colliding in the outer solar system, or at least this is one theory or hypothesis. And that this allows kind of the first surviving planet to form. And the idea here is that this is Jupiter, is that these 2 giant or bigger protoplanets in the outer solar system collide and become the first kind of dominant object in the solar system other than the sun. You see here the image that this is taking place in the outer solar system, where there's an abundance of gases as well that haven't been evaporated by the sun. And only a million years later, Jupiter has already gathered about 90% of its current size. So it's almost fully grown, and no other planets even exist yet. Shortly thereafter, in the next few 100,000 to several million years, we get the other planets, at least in the outer solar system, at least in one version of this story, which has Saturn, Neptune, and Uranus forming. You'll see the order there is actually different than today, and we'll get to that. Another mystery of the solar system is whether or not Neptune might have actually formed closer to the sun than Uranus, and then they switched spots, which is a possible scenario. And a few million years later, so 10 million years after collapse, most of the dust, that is to say the more solid elemental particles, is gone. And the solar system is starting to look less like a cloud of gas and dust and more like a bunch of rocks swirling around. We have protoplanets, planetesimals. Now we have 4 dominant objects, one of them very dominant in Jupiter. So we're starting to see. Now, in the meantime, the sun hasn't stopped doing what stars do, and that is that it's been evolving and maturing. And stars, by my understanding, and I'm certainly not a solar astronomer, or a stellar astronomer, I suppose, early on in their life, they seem to go through much more changes than once they reach kind of a stable process. So here we have 15 million years after collapse, which in one way, shape, or another could be considered the birth of the star. And nuclear fusion starts. So up until this point, much of the energy generated by the sun, or perhaps all of it, has been the result of friction-caused heat. So objects passing along one another, colliding, or at least having their fields collide and generating heat. But now there's enough pressure inside of the sun, gravitational pressure, that at its core, when 2 atoms meet, they actually fuse. And fusion releases infinitely, well, not infinitely, is a massively amount more energy than friction or fission. So nuclear fusion begins, and our star becomes the yellow dwarf, or an astronomy talk, G-type main sequence star, that it is today. So now, 15 million years after all of this started, we have a star, which pretty much looks like the sun today, and we have Jupiter, which pretty much looks like Jupiter today. We have Saturn, Uranus, and Neptune, which probably looks something like what they look like today. And the solar system is really starting to take shape to something familiar to what we've seen on posters since we were kids. And I would say that this chapter, this early chapter in solar system formation, really draws to a close with about 15 million years after collapse, with Jupiter having its orbit perturbed. We won't get into what, and there's lots of unknowns about why the orbits in the early solar system were so unstable, but just keep in mind that it's not the perfect system it is today. These things are moving around as big things form and pull on each other, and then those big things disappear because they get torn apart or they collide with something else. But somewhere in the process, Jupiter seemingly has its orbit tugged inwards towards the sun. And what this does is pull a bunch of planetesimals and possibly protoplanets inwards. The gravitational force of Jupiter moving inwards brings with it a bunch of little rocks. This may also have torn up any nearby objects. So imagine Jupiter moves in towards the sun, and on its way it happens to come closer to a planet that was forming, maybe an Earth-sized planet. And as Jupiter gets closer to it, the forces that were keeping that planet together can no longer remain stable, because now you have Jupiter's gravity pulling on it, and that planet to be breaks apart and never forms. And the combination of Jupiter flinging objects inwards as it comes in, as well as potentially destroying objects as it comes inwards, might be the origin of the asteroid belt. At the same time, possibly because Jupiter may also be taking objects from the inner solar system and flinging them out, or the other gas giants may be flinging objects outward as well, the Kuiper belt forms. And the Kuiper belt, as I talked about in last week's podcast, is this outer asteroid belt, which is kind of the border of our solar system, at least in terms of interesting things to look at. Beyond it, there's still a ton of space, which we still call our solar system, but it's almost entirely empty as far as we know. And the Kuiper belt's huge. It's much bigger than the asteroid belt, which is really just a thin ring of small asteroids. Kuiper belt, much bigger. There's actually little planets hiding within it, little moons, like Pluto and Eris and possibly others. But now we have the sun, the four gas giants, and the so here we have it, the solar system as it exists at this point, roughly 50 million years after the whole thing started. I know that sounds like a long time, and it would be for a human, but in astronomical scales, it's nothing. 50 million years is a split second. Keeping in mind that the universe is between 14 and 17 billion years old. Our solar system is 4.5 billion years old. 50 million years is very short, but of course for humans, it's very long. So we have the four gas giants, the star there. Ignore the yellow circle there that's showing the orbit of, well, it could be the orbit of Pluto, also the orbit of other large objects in the Kuiper belt. But we have the Kuiper belt, and also the asteroid belt, which on this scale would be so small you could never see it. So ignoring that object in the yellow orbit there, this is our solar system as it exists 50 million years after. All right, collapse. We're finally getting to Earth. So 75 million years after collapse, 25 million years after what we were just talking about, we have two objects. Rothery in his chapters is skeptical about naming protoplanets and assuming they're at all related to the current planets, but we're at a point in the solar system formation, at least in this part of the story, where we think it's fair to say that these two orbiting objects could be called Earth and Theia. So Earth, the same Earth we live on right now, and Theia being another object, probably about a quarter the size of Earth, so maybe the size of Mars. And they're both around the inner solar system. And 80 million years after collapse, they collide. And what we think happens here is that Earth kind of takes its size, or it grows to be the size it is today. So this is its kind of last collision. And in the reading this week, you'll hear that collisions were really the way that objects in the inner solar system formed. Whereas in the outer solar system, it might be a little different. Obviously, the collision that formed Jupiter is suspected to be one of the major collisions in the outer solar system, but there's also kind of gravitationally assisted accretion in the outer solar system. But that debate rages on about whether it was collision or accretion through gravitational attraction. Nonetheless, the story here is the collision between these two protoplanets. Earth gets bigger, and the debris starts to circle the Earth and form an early ring system. But this ring system doesn't stay, and eventually it self-accretes upon itself to form Earth's moon. And so Earth survives this collision, Theia does not. And essentially, the debris from this collision eventually snowballs gravitationally through its rotation into our moon. All right, we've got an Earth, well, the Earth in a sort of shape that it's going to be for the next 4 billion years. We've got Earth's moon, we've got the outer solar system, and in the inner solar system, by about 500 million years after collapse, and keep in mind all of these times are unsure, or uncertain, I should say, all the planets have formed. So we know a long time ago, almost 500 million years ago, the outer solar system planets formed, but by this point, the inner solar system planets formed. You'll actually see in Rothery that he's much more open to the argument of whether the inner solar system actually formed first, which would make Jupiter not the first object. Certainly plausible. Wouldn't really change the story too much. It would just change the order of a few things. And so now the kind of focus of the story is less on objects forming and more on objects stabilizing. So there's all these collisions, new objects are getting bigger and changing their gravitational influence on other objects, and everything's unstable. The only thing that's really stable at this point is the sun. It's powerful, its gravitational output is essentially the same, or its gravitational force, I should say, is essentially the same. But everything else is moving around and shifting, coming closer to the sun, moving farther from the sun, including Jupiter. And we think about, 500 million years after collapse, Jupiter is back into a phase where it's moving, it's continuing to move towards the sun, which would mean, again, as it passes things, it's either disturbing them or actually throwing them outwards. And at the same time, things that are behind it might be getting pulled inwards. And Saturn, Neptune, and Uranus are actually going the other way. They're arguably moving away from the sun. And as they pass things, they throw them in the opposite direction as well, which in this case would be into the inner solar system. All of this is still debated about how the movement of the great dance of the giant gas giants, how did that influence all the smaller objects, and was the majority of it small objects thrown into the solar system, so asteroids for the most part, or was it a much more of a process of small objects being thrown out of the inner solar system into the outer solar system? Certainly we'll see on the next slide that it makes sense that this jostling of the gas giants led to an influx of asteroids coming into the inner solar system. It would explain a few things. And we'll see how that before we talk about how this is affecting the inner solar system, we'll wrap up the outer solar system. So 700 million years after collapse, we get a kind of settling down. Jupiter and Saturn enter into a sort of orbital agreement. It's called orbital resonance, in which there's a stability formed between the two planets and, of course, the Sun, which acts as a major partner in this. And this orbital resonance kind of is a cascading effect of gravitational consistency throughout the solar system. It does act to push Neptune potentially outside of Uranus's orbit. So this assumes that we accept that Neptune formed inside of Uranus, and then it was pushed outwards by the orbital resonance of Jupiter and Saturn, and arguably, potentially another mystery, as it passed Uranus, it dragged it downwards and caused Uranus's tilt, which is, I think I discussed this earlier, but we'll definitely discuss it next week as well, and the week after as well. We'll talk about what we knew before the space age. Uranus is tilted sideways, so it's kind of spinning 45 degrees relative to all the other planets, potentially as a result of Neptune. This resonance also adds stability in terms of objects flinging in and out. And the solar system as a whole becomes much less busy in terms of material. And the solar system today is very empty in almost all places, except for things like the Kuiper Belt, or areas around Jupiter and Saturn. But for the most part, the solar system is very empty, and that's thanks to this process, again, roughly 700 million years after. So what did all this flinging of objects around do? Well, it did clear out a lot of objects, but some of those asteroids, I'll stop saying objects, I'll just say asteroids, they hit stuff. And this is known as the late heavy bombardment. And this is the arrival of outer solar system objects, as we think, pulled on by Jupiter, as it came inwards as well, coming in and hitting the inner planets. Now, why is this important? This is incredibly important, we think, for Earth possibly having materials that shouldn't be in the inner solar system, like a high amount of volatile gases, which make up our atmosphere and water, or oceans, I should say. So a lot of the materials that make up our atmosphere should have been blown away by the sun, should have been evaporated by the proto-sun long ago, but they're on Earth in abundance. And there's also evidence of them on Mars and well, Venus, we're not sure, but there's potentially volatile gases there. And these gases, which make up water and ice and the trace gases within the atmosphere, that give it the very healthy balance we need to have just the right amount of greenhouse effect so that we can live. These may have come to us by surviving in the outer solar system, so not being evaporated or blown out by the sun, and then getting tossed in via, so they would have settled on asteroids whilst they were out there, and then been tossed in. And that's how the Earth would have got much of its hydrogen and oxygen and methane and nitrogen. These things that are not basic oxygen silicate bonds, but other gases, or gases, I should say, that shouldn't have survived the inner solar system processes. This is one explanation offered to why the Earth has these materials. There were others that suggest that maybe these materials never were kind of evacuated from the inner solar system, but that causes all sorts of problems. So this late heavy bombardment brings outer solar system material into the inner solar system. Now the question might be, okay, so these materials come into the inner solar system. Wouldn't the sun just evaporate them or blast them away anyways? We're inside of the ice line, right? Well, now we have the Earth getting a little shield. And this is the result of the Earth's core being made up of iron and nickel. And as that core, which is not solid, but it's actually liquid, rotates, it causes an electrical field, which is something you can cause by generating friction between many forms of metal. So if you do that on a very big scale, the size of the Earth's core, you get a large magnetic field. And this magnetic field actually reduces the sun's impact on the surface of the Earth and allows materials like water, oxygen, nitrogen, methane to survive on the surface of the Earth. It also allows, to some extent, these same gases to survive on the surface of Mars and in the atmosphere of Mars. So the Earth and Mars have magnetic fields. We think Mars used to have much more powerful one, but it doesn't anymore. You'll see that in the next slide. Mercury has no magnetic field. And as a kind of confirming piece of evidence, Mercury also has pretty much no volatile gases on its surface. There might be some trapped in ice deep in craters so that the sun doesn't hit it. But, you know, aligning with our story, Mercury has no magnetic field, so it has no atmosphere or oceans, because these things would just be blasted away by the sun. Whereas on Earth, those things are protected by the magnetic field, which you can think of as a sort of shield, which protects us from much of the sun's most powerful radiation. Gigantic mystery being Venus. Venus has a very thick atmosphere, but it does not have a magnetic field. So what is happening? Well, maybe Venus's atmosphere is generated by a constant flow of volcanic activity, which keeps material around it. Maybe a magnetic field is not necessary for an atmosphere, although that I think would be a much more controversial statement. So the inner planets all have different stories when it comes to magnetic fields. The outer planets all have very strong magnetic fields. So as they were forming early in the outer solar system, they would have nabbed up the materials to make up iron and nickel. That iron and nickel would have sunk to the bottom of these forming Jupiter and Neptune objects, and you would get giant magnetic fields formed by these much larger planets than Earth. So, as you could probably imagine, the questions that arise from just this basic principle of magnetic fields is a big part of planetary exploration, and especially Martian exploration, though Venus as well. So we'll come back to that at the end.
In the not-too-distant future, scientists may be able to simply scan a star for Earth-like planets and find the signature of life there.
We can look right at the light from a little planet around its distant star, and that opens up a whole range of possibilities for us to not just detect the planet, but to study the planet.
I mean, this all sounds like science fiction, but there is a reality to this. We have a scientific method to actually determine whether there is life on another planet.
Life is one thing, intelligent life, another altogether. That requires billions of years and a powerful force field like the one we owe our lives to every day. If an alien astronomer were to file a report on our home solar system, they might make a surprising observation. Because of all the 8 planets that orbit the Sun, they could easily conclude that 2, not 1, were suitable for life. It's an easy mistake to make, because the Sun has 2 planets within its Goldilocks zone, the Earth and Mars. Both planets have surfaces warm enough for liquid water to pool on. But while the Earth is blessed with warm, liquid oceans, Mars is dry and dead. The one crucial difference between these 2 planets could be the key to finding truly habitable exoplanets: a magnetic shield. Our sun is constantly hurling deadly radiation out towards us. Only our magnetic shield, the magnetosphere, saves us. Without it, the solar wind would blow our atmosphere away, and without an atmosphere, liquid water could not exist on the surface.
In order to have liquid water, not only do you need the right temperature, but you need the right pressure. You know, if there were no atmosphere here right now, even at the same temperature we are today, all of the water would boil off into vapor immediately.
So where does the Earth's magnetosphere come from? And why doesn't Mars have one? Actually, in the past, both Earth and Mars had magnetospheres, but Mars lost its around 4 billion years ago, and with it, the potential for life. Both the Earth and Mars were born into a realm of violence. Asteroids smashed into their surfaces, turning rock and metal into a molten mass. As they started to cool, a solid crust formed on the surface. But the molten metal below churned as the planets turned, inducing a magnetic field which rose high up above the surface of both planets. At the same time, active volcanoes pumped gas into the space around each planet. Protected by the newly formed magnetic field, these gases built up into thick atmospheres, creating the air pressure for liquid water to run on the surface. For over 100 million years, both Mars and Earth were warm, wet paradises, primed for life to take off. Then, quite suddenly, Mars's magnetic protection disappeared. The solar wind blew its atmosphere into space, and its oceans boiled away, leaving the dry, sterile red rock we see today.
This kind of brings us to the end of the story. We've only gotten to about 700 or 750 million years after collapse. But I said collapse happens 4.6 billion years ago. So that leaves us 3.9-ish billion years. Well, from a planetary formation, from a solar system formation perspective, really nothing's happened in almost 4 billion years. From the perspective of our solar system as a whole, if you were observing it from a distance, it's been essentially the same for 4 billion years. It was just really busy for the first 500 million years. Now, for Earth, that's not the case. And for any one individual planet, that's not the case. Each planet is its own little system itself, and it's undergone a ton of changes. The Earth is no different. So the Earth has gone through a series of geological transformations, the evolution of plate tectonics and continental drift and supercontinents and snowball Earth events, which is this really interesting phenomenon hypothesized in which the Earth is covered globally in glaciers and then breaks apart, goes back to being water covered and back to just glaciers, global glaciers. And all sorts of interesting knowns and unknowns about the Earth's own history over this 4 billion year period that we're not going to talk about. Dinosaurs, asteroids hitting, the evolution of humans and life, of course, and vegetation and the fundamental changes in the Earth's atmosphere as a result of vegetation. All of that happens. None of that really matters to us. We know where we are in terms of there being plants on the surface of the Earth. So the main part is what happened in that first 700 million years or so. How did the solar system form to get to where it could start having all of those other things that geologists study about Earth and biologists study about how life formed and all that? So that's the solar system. It's essentially very, very stable. Its orbits are incredibly stable now. Not too much is going to change. We're not going to see Jupiter. Well, maybe I shouldn't say that. We're not going to see, the Earth just get another moon out of nowhere. We're not going to see Venus break apart. Very fundamental changes like that probably aren't going to happen in our lifetimes, and by our, I mean human civilization. So the next big changes will happen when the sun starts undergoing changes in 4 billion years. And we might see things like some of the rings around Saturn form into smaller moons, which we're already seeing. But we're not going to see fundamental changes to our solar system to the extent that have happened in the past. One reason for that is that the human lifespan and even the civilization lifespan is so much shorter than how long these things took. Remember, it took at least 100,000 years for something like Jupiter to even, from its first kind of early inkling to becoming even something slightly bigger, is 100,000 years. Well, that's almost all of human civilization. And that's just a tiny, tiny little speck of Jupiter, never mind the whole thing, which takes 6 million years to form, or at least 4 million or so. So that's the story of the first 700 million years of the solar system, the origin story of the solar system, if you will. And though we're here now, there are still questions. As I've hinted throughout the process, a lot of this is unknown, right? It's really hard to go back in time 4 billion years using things like meteorites, using, drill cores of the Earth, using little analysis of the sand of Mars and stuff like that. It's really hard, but we have been able to piece together a story that makes sense and aligns with the universe as it is today. So in science, that's usually a good hypothesis. But there are still questions. And that's what space exploration is all about, answering some of these questions, both for pure scientific reason, but also to make things better here on Earth, whether that's through technological development or whether that's through a more philosophical approach of having us know where we come from, or whether it comes to scientific understandings or breakthroughs that lead to other things, right? We understand chemistry better by understanding the changes that methane takes at different parts of the solar system. There's all sorts of benefits or reasons we do this, not the least of which is helping to fill in this puzzle, this story that I just told you, which obviously has giant gaps in it. Some of those include, what are the cores of planets definitely made out of? And why do we get magnetic fields in some, but not others? And why do those cores sometimes stop working, as we saw with the video about Mars? And why would they happen on different scales, right? If Mars and Earth may have formed around the same time, their cores should have formed around the same time. Why is Earth's core still going strong, but Mars is not? Mars is smaller, is that maybe it? But Venus is roughly the same size of the Earth and should have formed around the same time. And Venus's core doesn't appear to be giving off any magnetic field. Does it have an active core that for some reason doesn't give off a magnetic field? We don't know. Asteroids are always interesting because there's a chance that they might be very old. They might be asteroids that are still surviving from 4 billion years ago that never crashed into anything or never crashed into Jupiter or Earth or another asteroid. And in that sense, they give us a clue into the earliest chemistry of the solar system. And that's, critical to answering a lot of these questions as well in terms of what elements were around and which ones were not. Moon, our moon, how it came to be, of course, that giant impact that I told you about, that's one hypothesis. It's by far the most, it's the strongest hypothesis by quite a bit. But, there have throughout history been other ideas about how the moon formed. And the way we've come to the current conclusion is a great example of the role of planetary science. The Apollo missions were incredibly important, as you'll hear in a podcast later this year, about giving us an understanding more definitively about how the moon formed. For those really interested in astrobiology and whether or not there's other life in our solar system, or if there ever was other life in our solar system, or could be, remember that our solar system might have a lifespan of about 10 billion years. We've seen 4 billion so far, and certainly we're here. Could there be other opportunities for life? Could there be the potential for life bubbling under somewhere else in the solar system? And what ingredients are needed for that? Why did it happen on Earth? Did it happen earlier on other planets, and it's long since gone, and we came along later. That's a fundamental driving question of a lot of planetary science, certainly a lot of exploration of Mars, driven by the idea of, was there ever life on Mars? We see an atmosphere. We see some of the ingredients, if not all of the ingredients for life. Was it ever there? Could it be there in the future? Is Mars on its way down from being habitable, or is it on its way up? The argument most often is it's on its way down. It could have been warmer in the past, especially if it had a magnetic field, but we don't know. Even things like tilts, rotations. Why do planets spin and rotate at the speed they do? What's the impact of tilts and rotations on the surface processes? Obviously, for the Earth, our tilt gives us seasons. Seasons have been incredibly important in the evolution of life and the survival of life. And earlier I was mentioning the hypothesis about snowball Earth. Seasons have been critical to that hypothesis. And if the Earth ever did undergo long periods of freezing, the fact that we have a nice 23 degrees tilt might have been critical until allowing early melting and then full melting, so that we didn't just stay an ice ball. And even just something as basic as dynamism. So Earth is by far the most dynamic, that is to say, active or complex body in the solar system. Nothing, I don't think, even comes close to the Earth, because we have life, and life is in itself an incredibly dynamic system in which it changes on a daily basis. So the Earth's surface, compared to other planets, looks different every day, right? A lot of that's because of life, but we do have vegetation, which no other planets have, which means our surface pretty much looks different every day. But other planets are dynamic in different ways. We think Venus has potentially active volcanoes, potentially flowing lava, which would mean an active, busy system. Mars might have ice melting and forming, and that's a form of dynamism. Whereas we know something like Mercury or the Moon is essentially dead. And when we say dead for planetary bodies, we mean there's no dynamism. There's nothing happening, or at least on a human scale, right? So the Moon, there's still daylight, so there's still day and night, which means you get the sun hitting some areas versus others. So you could get ice melting if it happens to hit ice that is only seasonally tilted a certain way. But for the most part, nothing happens on the Moon on a daily basis. Or on Earth or Venus, or even Mars, thanks to wind and stuff like that. There's stuff happening every day, and that's a big part of planetary science as well. Of course, the gas giants are giant gas balls, they're really, a better way to think of it is giant atmospheres. And atmospheres are, of course, dynamic as well. So Jupiter's big red spot is changing. We've seen it shrink. It's on its way to no longer existing a few hundred years from now. So dynamism is a big part as well. Understanding these changes in planets and what's causing them can give us clues into how they formed, as well as the fundamental forces of our universe. So I'll leave it at that. That's the formation of the solar system. And I hope you understand now the importance of this. It really is the base storyline. It's like the driving mystery of space exploration and of this course. There's other things like what kind of technologies can we develop to explore these things, which is kind of like a secondary question. But at the end of the day, especially for a lot of scientists, it's about what is this system and how does it work? And this is at the beginning of a lot of movies, there's a key mystery, and then the movie plays out, and at the end they solve the mystery. Well, planetary science is kind of halfway through that movie or less. We know the mystery. How did this system get here? How did the Earth get here? Why is there life on it? Whatever question you want. And we're kind of working our way towards solving that mystery. When we will, who knows? But in the meantime, it's incredibly interesting, and it also improves things here on Earth in various ways. So hope you enjoyed that. And the next one of these virtual lectures will be much the same. I'll probably just do a video on the intro and outro, just so you see my face. But for the most part, it's going to be either videos I upload or my voice.